Welcome everyone to the One World Combinatorics on Words seminar. Our speaker today is Jamie Simpson, and he's going to speak to us about palindromic periodicities. Oh, sorry, I think we lost your screen there.
I've lost the screen, full screen. Um,
Can you try resharing?
Whereabouts is that? Oh,
So,
sorry, sharing it. Yeah,
yeah.
right. There we are. Oh,
Aha, there we go. Perfect.
okay.
Thanks. Yeah, all right. I'll let you go from here.
Right, okay. Well, hello everybody. The title is Palindromic Periodicities, and I'll explain what they are in a minute. But that's I made a name it myself, and I don't think it's a very good name anyway, and it's very hard to say too. So it's doubly bad. Um, uh, Sorry, having trouble with changing the. There we are. Okay, so we're using the usual notation for combinatorics of words. RW is the reverse of W, W is a palindrome, and W is a palindrome if RW is equal to a W. So the ABA and CC are palindromes. Empty word is epsilon, and that's also a palindrome. Well, the definition of a palindromic periodicity is as follows: that if P and S are palindromes, and W is a word of length at least PS, and it's factor of PS to the omega, so an infinite concatenation of PS, then it's called a palindromic periodicity. And there's some examples, or an example, using palindromes ABA and CC, and then we concatenate those together and get a thing, ABA, CC, ABA, CC, and so on. And if we chop out any factor of that, of length at least 5, which is the sum of the lengths of those two words, then that's a palindromic periodicity. The way this talk is going to work is I'll first of all talk about some simple properties of palindromic periodicities. I'll then talk about how they arise, and they're not just things that I've made up, they do occur naturally. And that is a periodicity, so it's like the ordinary periodicities, but with a few extra wiggles on it. So what I'll derive is something like the fine-Wilf periodicity lemma, but applied to these things. And that's the sort of main part of the talk to get there. I'll then have a discussion about some of the ways which we can carry on research on these things. It's a bit of more notation about palindromes. We say that a palindrome is odd or even, depending on its length. And it has a center, which is I plus j over 2. And that's an integer if the palindrome is odd, an integer plus a half if it's even. So if it's even, the center lies between two letters. And if it's odd, then the center coincides with the letter. In either case, we have this identity for finding out what things are equal to each other in a palindrome. That's W of 2C take K, that's 2 twice the center, take away K, is equal to WK if K is lying inside the domain of the palindrome. And we also have this identity palindroming nested as another palindrome. And there's a bit of algebra there, but the example there is clear of what's going on, that CD, EDC is a palindrome sitting inside that longer palindrome. and DED is all inside it, and E itself is inside it. We say that, this example again, that CABACCA is a palindromic periodicity as its factor of that thing, with P being ABA and S being CC. But it's also a factor of the palindromic periodicity with the palindromes being B and ACCA. You can see that with the example at the top. And also you have it that in this case that one of the palindromes is empty, and we're just having the other palindrome is the whole of the period, CABAC. What this means is that knowing the periodicity doesn't determine what P and S are. However, the two things that it does determine are the centers of the palindromes, that centers between the two C's or and between and coinciding with the B, and also coinciding with the epsilon in the last case. So that the centers are fixed for no matter how you choose the palindromes themselves, and also the distance between them is fixed, which is half of PS, length of PS. And these centers of the palindromes are called essential centers. That's to distinguish them from other centers, palindromic centers, which might occur in the word. So that in this example below, the essential centers coincide with the C's and the D's. There's also a palindrome BB appearing in it, and that's got a center. It's not an essential center. Each essential center is the center of a palindromic prefix or a palindromic suffix, so that the center of the BB on the left there is the center of the the center of the C on the left there is the center of the palindromic prefix DABBC so here each C and each D is a essential center. The palindromic centers between with 3 E's in it. Each pair of D's sort of centers, but they are not essential, and they're not centers of palindromic suffixes or prefixes. Right. So where do palindromic periodicities come from? Simplest one is where you've got a word which is both a palindrome and its periodic, like those examples there. The things look fairly similar, but they've got different periods with both palindromic periodicities. The structure of them differs when one's odd and one's even. It also differs when the period is odd or even, but they're doing roughly the same pattern for each of the 4 cases. I think I'm going to finish this very quickly. I'm rushing through these. Okay. The other thing, this is the more important theorem of where they occur. When you've got 2 palindromes which contain each other's centers, and neither is a proper factor of the other, then their union is a palindromic periodicity. With half period is equal to the difference between the centers. That's something I should have said a moment ago. The period is what you expect the period to be, but the half period is the distance between the essential centers, and that's sometimes a more useful parameter to work with than the actual period. But in this case, we've got 2 palindromes which are shown by those braces. They're both even length, so they're pointy bits in the braces of the centers. To see how this theorem works, I'll shove in some words, some letters in between the two centers, just there. That ABCD is now reflected in the center of the top palindrome. So we get this, which is starting to look like it's a palindromic periodicity already. That thing is then, or at least the CBA ABCD part, is now reflected in the bottom brace, or bottom palindrome, is there. And then part of that's then reflected in again in the top one. Oh, going backwards. There we are. So that's how it works, and you see that you have got a palindromic periodicity. The half period is the length of the ABCD, which is 4, and that's the distance between the centers. There's one extra bit here. That's a bit interesting that we've got two palindromes making a periodicity. We can also have two periodicities making a palindrome. And this is with this theorem, which is, I imagine, well known. I couldn't find it anywhere, but it's not hard to prove that if you have a word having two periods, P and Q, with the greatest common divisor being 1, and its length, P plus Q minus 2, and that's 1 less than the it's needed for the Fine and Wolf palindrome lemma to apply. Then it turns out that the you get a word which is a palindrome. And below there is an example with 5 and periods 5 and 9, giving a length of 12 is P plus Q take 2. So that's giving us a palindrome out of 2 periodicities, whereas the previous theorem gave a periodicity out of 2 palindromes. Okay, I'm going to finish very quickly. This is going towards a palindromic periodicity lemma, which is like the Fine and Wolf periodicity lemma. So we first of all we can describe a palindromic periodicity by the positions of its essential centers, and these are h apart, so they're sitting in an arithmetic progression of that form k plus ih. H is the half period, and we call k the offset of the palindromic periodicity. We're interested in a k and h are in z over 2. Z over 2 means the integers divided by 2. So z over 2 means the integers plus the set of integers plus a half. And both k and h are in that set. A double periodic periodicity is a word which is a periodic periodicity in 2 ways with different parameters, k1 and h1 and k2 and h2 for some parameters. And what the lemma turns out to be is looking rather like Fine and Wolf's periodicity lemma, which is given there. So a period's got word's got 2 periods and sufficient length, then it will also have a period of the greatest common divisor of the 2 periods. Our case is this: the if it's greater than that, that's the 2h1 and 2h2 are the 2 periods. That's the sum of the periods plus that greatest common divisor. And that's looking very like the Fine and Wolf period. And it's Fine and Wolf length restriction. The periodicity is also looking very like it. for Feynman Wolf, the periodicity would be the greatest common divisor of 2H1 and 2H2. But we've got this extra factor of 2 times K2 minus K1 in it. And the length is very similar to the Feynman Wolf case with a 2H1 plus 2H2 minus the greatest common divisor. And it's a periodicity, and it has opposite K1. This this is the half period for the new whole palindromic periodicity. But we could have any one of the essential centers being the offset, using the idea that the greatest common divisor of these two things is just equal to that. And that means that we can add on multiples of 2H1 and 2H2 to the 2K2 plus minus K1 part and have anything like this, like the bit at the bottom, as the greatest common divisor. And we'd have anything like 2K2 or like K2 plus M2H2 and K1 plus M1H1 as being the essential centers we use to set up the palindromic periodicity. So K1 and K2 can be replaced by any two essential centers of the two palindromic periodicities. Okay, this is now an example. In this example, I've got the two half periods are 6 and 4, I think. Um, a 6 and 4, and that means that the difference between the centers is divisible by 4 in each of these choices of K1 and K2. I've got all the choices of K1 and K2, which will have a difference of an even difference, which means that the difference will be divisible by 4 when we multiply by 2. And that means that the greatest common divisor in this case is 4. The length that we get from the theorem on the previous slide is actually equal to 16, which is at the top there. And as the theorem says, we get the greatest common, the period is 4 in each case. And that's what the theorem says. That's sort of reassuring. It's always nice if our examples agree with our theorems. If we were dealing with Feynman Wolf here and looked at a word which was one letter shorter than the period, some of the periods minus the greatest common divisor, we'd find that the period was greater than the greatest common divisor. And that means that the Feynman Wolf is sharp, and that'd be sharp in all cases here, or sharp in many, or sharp. However, with us, things aren't so nice. In this case, we're sharp when K1 and K2 are equal to 0 and 2, but not sharp otherwise. If we look at the other lengths, it's even worse. The periods are now all over the place. And I think that this with a bit more work or a bit more energy, somebody could clean up my theorem to show us where all these 8s and 4s are coming from, and the bits at the end, which are the 7s and 6, come out of the fact that the palindromic periodicities which went into it did have periods 7 and 6. So now I'll talk about things which is how we can extend these things. There's various ways we can investigate this. The first one is just to strengthen that periodicity lemma. That would be nice to get a full description of what's happening rather than just what's happening in the first column of my last table. The next thing we do is look for palindromic periodicities in famous words like Fibonacci words and two-Morse words, Sermian words, and various other things. These are the sort of things that people have done with periodicities in ordinary periodicities. The next one is the next one is to find an efficient algorithm for searching for palindromic periodicities. The way I did it was a very clunky way of actually looking for runs or looking for periodicities and then checking to see if they're palindromic to periodicities. But I mentioned there's a much smarter way of doing it than that. The next one's that's what I left nothing. Next one's a bit more complicated. There's a well-known and easily proved theorem that a word length n contain at most n distinct non-empty palindromes. That's famous theorem and it's easy to prove, got a very nice, beautiful proof. In a paper called Palindromes in Circular Words, I tried to do the same thing with palindromes in circular words. This turned out to be much more complicated and didn't give a sharp bound. Well, I couldn't get it. I showed that any circular word of length less than any circular word of length n contains at most less than 5n over 3 distinct non-empty palindromes. This is because it's all the same palindromes in the first n places. You can get other palindromes which are lapping around the ends of the word, overlapping the ends of the word. If n is actually a multiple of 3, that means that the word contained most 5n minus 3 distinct non-empty palindromes. However, I think it's less than that. By construction, I created words of length 5n minus 3, 5n over 3 minus 2 distinct non-empty palindromes. And I think that's the best you can do. It was from a computer search, and that turned up in a very simple way, the words which produced that at length, but nothing which was longer than that. For words which are not multiples of 3, the situation is a bit more complicated. The examples I looked at didn't have a nice pattern, but maybe a nice pattern would emerge if I went to longer examples. What this has got to do with palindromic periodicities is that in that paper, I used a weaker version of the overlapping palindrome theorem. That's the theorem about if two palindromes contain each other's centers and then the union produces a palindromic periodicity. The weaker version was one where I just said that it produced a apparent periodicity without knowing that it was, or noticing that it was palindromic periodicity. And I came up with the idea of a palindromic periodicity by seeing that the periodicities occurring here did have this special structure. And it's possible, it occurred to me that this new improved version of the overlapping periodicities lemma might give me the extra edge to close the gap between those, the 5n over 3, take 1, and the 5n over 3, take 2, and show that, in fact, 5n over 3, take 2 is the correct one. I haven't been able to do that, but maybe somebody else can. And the final thing is to do with a thing called things called maximal periodicities. This maximal periodicity is periodic factor in a word which whose length is at least twice its period, and that cannot be extended to the left or the right without altering the period. or without going over the edges of the word. This had a quite a lot of interest in it back in the dates got there. Um, Ryan is the maximum number of is palindromic periodicities, maximal periodicities rather, which are called runs, which can occur in a word of length n. The business started with Popukov and Kucherov, who showed that rho n was equal to big IN, but their method didn't have any information about the size of the implied constant, and they conjectured that rho n was actually equal to n. That became known as the Runge conjecture, and then there's a series of people who improved it. First to 5n, then to 3.48n, and to 1.6n. Then Giro with those two values. And finally with Kroshmore-Nilly, or not finally, then Kroshmore-Nilly with 1.029. Then the big breakthrough, which actually proved the conjecture but did more than that, was by D.O. Benai and his colleagues. And they proved the conjecture. But what was really spectacular there was that their original proof that I saw of theirs was about 3 pages long. It was absolutely brilliant, very short. And that compared with Crushmore's Lilly's paper before that, which was a long, or not a very long paper, I think it's about a dozen pages, but I found it very difficult. It was also backed up by nearly 3 years of CPU time to verify to verify the calculations. But with the Benai and those other people, there was no computers involved at all. Just something where the argument would be written down on squeezed into a page. Then Fish and Holub and the other two, I there as the Japanese name, which looked a bit odd, Levenstein, brought it down to 0.957, and that was using computers. And I think that's the best it's been done, but I might be wrong there. And then my question is, could we do the same thing with maximal palindromic periodicities, defined in the same way? And if people are energetic to go through those same steps to get a palindromic run theorem. And that's it. So thank you for your attention. And I'll answer any questions. My hearing's not very good, so it may not be good, but please go ahead and ask. Do I need to push any buttons?
No, no, that's perfect.
Okay.
Thank you very much, Jamie. Thanks a lot. So, yeah, Jamie will be happy to take your questions. Also, maybe I'll just mention that Gabriele wrote in the chat, he gave a reference for that result about a word having 2 coprime periods and length 1 less than the fine wealth bound.
Well, thanks. I'd
So
like to see
yeah,
that. Yeah.
he gave a reference to in the chat if you want to have a look at
I'm
that.
sure somebody would have seen it before me.
So does anyone have any questions for Jamie? I mean, do you have some sort of conjecture for that maximal palindromic runs?
No. No, not at all. Except that it's going to be less than the ones for runs, ordinary runs.
Okay.
No, I didn't do a lot of calculations of that because my way of recognizing palindromic periodicities is so clunky. But with a smart way of doing that, then you could get some examples, some decent sized examples.
Hmm. Oh, Jeff, yeah.
Yeah, just just playing around suggests to me that maybe every factor of every Sturmian word is a palindromic periodicity. My guess is that if that's correct, which it might not be, but if it's correct, it's probably relatively easy to prove using known things about Sturmian words, since we know so much about Sturmian words. But that would be fun.
Yeah, yeah. I'll have a look at that.
Um, Gabriella has a question.
Gabriella,
Yes. Hi, Jamie. How are you doing?
hi.
My question is about the result you gave on the half periods. Is it correct what I understood that essentially what you get in palindromic periodicity is a period that a period as a word that alternates with its reversal. So word reversal, word reversal, word reversal as a period.
Um,
Like
Sorry, I don't understand it.
in the example you showed,
Yes,
if you can come back with the slide with the two overlapping palindromes. Yeah, this one. Okay. Here it seems that what you get is that instead of having a periodic word, you have a word in which the period alternates with its reversal.
that's true. Yes, yep.
Is it a characterization of palindromic periodicities?
Yes, it would always be true that um, well, except with when it's not um, an odd length palindrome, you get a sort of isolated letter in the middle.
Ah, okay,
Um,
I see. Okay,
yeah, the same thing on each side of the middle.
okay, thanks.
Does anyone else have a question? All right, if not, thank you again, Jamie.
A pleasure. Thank you for inviting me.
Appreciate you joining us at this late hour for you.
It's not too bad.
And thank you, everyone, for coming today and for attending the seminar this year. I believe this is our last talk before our little summer break, and we'll pick up again in September.